2212, Lab 4, Magnetic Braking with Faraday's Constant by Lucy Backer. So a little overview of what we're going to be looking at in this lab presentation. So we'll go through an introduction, the fundamental physics principles used in this experiment, and then we'll look at the experimental setup and the computational experiment. And then between those two different results, we'll have discussion points in comparison. And then finally, we'll go through the conclusion questions. So for an introduction purpose, so we want to collect observational data of a magnet falling through a conductive tube of aluminum foil. And to do this, we'll be literally dropping a magnet through a circular tube of foil, aluminum foil, and we can assume that there's going to be an interaction between the two, which will cause a delay in the fall. And so we can model this, the magnet tube interaction computationally, and then compare it with our actual experimental data and compare if there's any differences. And then for the results I obtained really small numbers. It might be a fluke, but my average time magnet was in the tube was 0.341 seconds, and the computational model's time was 0.254 seconds. So for our main physics ideas, so Faraday's law, here I have in both differential and integral form, which I'm not going to read through because, and then we have Newton's second law, so F equals ma, and then we have the Biot-Savart law, which is also really long, so I'm not going to read through. And so for the experimental setup, so our system is the magnet, and the surroundings is the aluminum foil and everything else. So first step we did was we marked the magnet's poles, so the north and south pole, and then we created an aluminum tube and we took the diameter measurements, and then we held the tube upright and recorded the time it took for the magnets to fall through. And we repeated this 5 times and we took an average. And then to create our computational model, I'll show you how I incorporated the physics ideas earlier into coding. So here we have just a little diagram for you guys. So we have the tube, and then we have the magnet, and you notice that we have the force of gravity, and also note that FB increases as the magnet falls down because the interaction becomes stronger. So for my coding, the first thing I did was we inputted the length of the measurements we took of our tube, so the length and the width of the foil, and then it calculated for us everything else. And then we also had to input the equations for, first of all, the magnitude of R, and then R hat equations, and then that would be able to give us what B is. And then here we also had to make set up the equations using, again, the physics ideas and Biot-Savart law and Faraday's law, which is also included here for magnitude of force on ring, magnitude of force on magnet, and our B hat. And then this was the result I obtained, which shows the 0.254 seconds, which compared to our data is slightly smaller, but that's expected considering that there was a the coding doesn't take into account everything, which here I can talk about more of it. As I was saying, there was a slight discrepancy, so the source of error or uncertainty could have been that the computational model doesn't take into account air resistance. There was also a reaction time of the experimenter for when I would count the actual time when I was taking the experimental data, which could have caused a lag. And then also the tube length measurement could have also been an error. I only have with me a pretty flimsy ruler, so that's really possible. And also it's not a perfectly flat surface to measure. And then also the magnet may have touched the tube or grazed it a little, which would have slowed it down. So for our conclusion questions, what if resistivity of a conductor were reduced as close as possible to 0? How would dynamics change? So it would cause an increased magnet force and induced current, and therefore a slower fall. And then what if holes or slots cut into the tube? How would this affect the ring currents in your model? So less aluminum foil would result in lower magnetic force and induced current, so magnet would fall quicker. And thank you for listening.